really hard to teach in Unit 3 about cells. They're the ones that are going to be on transport, which is going to be the first lesson, and the one on osmosis, which is going to be our second lesson. These two are often confusing to students because what you say in the first lesson sometimes feels like it contradicts what you say in the second lesson. And so I want to point out the misconceptions that students tend to have when we go over this. So the first lesson is going to be transport. This one, I always focus back on the bigger idea of structure function, which is how something is made is related to what it does. And so I always come back to the really simple idea of like a fork and a spoon. They have very similar structures. One is kind of bowl-shaped, one has pokey prongs, and their function is going to be different. One you can stab your food with, one you can scoop your food with. And so it kind of gets that idea for students looking at how things are made and what they're doing being very closely related. So if you have like kids who are on sports teams, you could talk about the difference in cleats between like golf and soccer and baseball and football cleats and how the structures of those, may help prevent injury or help with better performance. And you can look at things like vehicles. So like a really big pickup truck and a sports car, they all have the same parts, but they're going to be different shapes and sizes, and that may influence how you're going to use this vehicle. And then to try to bring it back to what we just learned about, we could talk about cell parts. And so certain cell types have certain cell parts. So like a muscle needs a lot more energy, so it's going to have a lot more mitochondria. A animal cell needs to be mobile, so it's not going to have that cell wall, but a plant cell might need a little more structure, so it has that cell wall. So how do we relate how something is built to what it does? Right? And so the idea that we're trying to get across here is first this idea of selectively permeable. So the analogy that I tend to use here with selectively permeable is the room that we're sitting in. All right. And so there's lots of walls. All right. Most of the walls that we're going to be in are made of brick or drywall or whatever room you happen to be in. There's some solid thing that's keeping everything in and everything out. But a room is not really useful if everything is being kept in or everything's being kept out. We got to let some things in and out. And so a cell membrane is selectively permeable. A lot of times we use the analogy of like a security guard or like a TSA agent as kind of looking at stuff and making decisions. But the way that the membrane works is much more dependent upon its structure, very much like the walls in this room are. So if we think about things that we want to get into this room, things that we want to get out of this room, we have to embed little things in the wall. So we're going to have things like doors, and sometimes the door can be open, sometimes it can be closed, and it's going to function differently. Windows are going to be sometimes open, sometimes closed, and they're going to operate differently. You might have air vents or a speaker or an outlet or like an Ethernet jack or a cable plug or a telephone jack, all those types of things. So I like to try to bring analogies between like what it is in our wall that's going to allow things in and out. Sometimes we want sound to be able to come in and out, but nothing else. So we're going to embed a speaker so we can have the announcements in there. We might want electricity to come in and out. The only way to really let electricity go through the doors or through the walls is even if we have these doors, windows, air vents, speakers, it's really only when you plug that outlet in there that it's going to let electricity come in and out. And so lots of different things. We could talk about doors being open versus closed and what they do and don't let in, or windows being open and closed and what they do or don't let in. Air vents, we want, fresh air. We also want heat or cold, depending on what time of season it is when you're teaching this. And so this is kind of that idea of selective permeability. We're in a room. This room is going to let certain things in and out. And because it's a classroom, it's going to have certain things. Right? At home, you might look at your closet or your bathroom, and they're going to have a different number of doors or a different number of windows or a different number of outlets. Like your bathroom, probably not going to have a lot of windows in there because we don't want light coming in and out. We don't want a lot of people seeing in and out of the bathroom, and it probably doesn't have a whole lot of outlets, right? Same thing with your closet. Probably only one door, probably not a lot of outlets, probably not a lot of windows in your closet. Whereas if we look at like your kitchen, you probably want a lot more outlets because you have a lot more appliances, and you might have some windows in there to let some light in or some air in. And so the idea of selective permeability can be linked to this idea of rooms, and the walls keep things in and out. But there's usually all these other things that get embedded in there to make these walls in your rooms selectively permeable. Right. And so to get this idea of structure function across, you can talk about other things that let things in and out. So you can talk about a colander. You might want to talk about that thing that little kids play with the shapes, all right, or an air filter, which will let certain things through but not others. So spaghetti gets stuck in a colander, but the water goes through. If we want to look at more complicated areas to kind of think about things, we can think about recycling and filtering. And so, like, we can filter objects by do they float or do they sink, or are they magnetic or are they not magnetic? And so, other than just size and shape, there's other characteristics that allow things to get in and out. And when we talk about the membrane, we're going to talk about polar and non-polar. So this idea of like floating and sinking, or magnetic, not magnetic, really gets into this idea of properties, chemical or physical properties, really being used to sort. All right, if you want the kids to kind of take their brain in a different direction, we can look at like 5 different types of fences. Barbed wire fence, kind of our traditional like farm fence where it's slats. We got chain link, we got wood fence, we got these wrought iron fences. Like, what's going to get in and out? Can you see through it? Are you going to let people through? Are we trying to not let cows through? Like, what is the purpose? And is its structure? How is it related to its function in letting things be selectively permeable? So I try to set these ideas as kind of like that accessing prior knowledge, that APK, to kind of get this idea of we want things to come in and out, and the structure of how these barriers are created are going to let things in and out. And so when we talk about that, we're then going to follow that up with passive transport, where we talk from high to low. High to low is extremely important when talking about diffusion. And this comes back later because diffusion and osmosis, to a lot of kids, feel like they contradict. And so we're going to really stress this point of diffusion. Things move from high to low. Diffusion can be pretty much anywhere. You can talk about a smell. You spray some Axe body spray in a corner. It has a very high concentration. It's going to move out to a low concentration. All right? So smells will move from high to low. Molecules have a tendency to move from where there's a lot of them to where there's less of them. They don't decide. It's not like all the molecules look at each other and go, oh, you're here, I'm here. No, we just have to move pretty randomly. Like, it's random motion from high to low. Facilitated diffusion goes back to a lot of these ideas. We can link back facilitated diffusion to our selectively permeable idea of, well, we have a window, maybe it's a smaller window, so humans can't get through this window when we open the window, but maybe some air can get through the window. All right, maybe we have a high to low concentration that we don't want. So there's a lot of bugs outside. It's that time of year there's a lot of mosquitoes or flies. And so we might want this to be selectively permeable and close our window so that these bugs are not moving from high concentration outside to low concentration in our house. All right, or pollen. Maybe we start to, if you have a lot of allergies, you start to close your windows because all the pollen comes in. So this idea of facilitated diffusion of only things can kind of get through certain openings, and it can't go through the wall itself, but it can go through these little openings that you happen to have in your walls. All right, so we talk about high to low, and there's like a net diffusion. And so let's say you've got a whole lot of stink in your house. Like maybe you just burnt some popcorn. All right, and so you have this stinky smell of burnt popcorn inside your house. You're going to open up the window and it's going to go from high to low inside your house to outside your house, but it's not going to get all of it out there. It's just going to keep getting less and less and less of it until you can't smell it anymore. So the more windows you open, the faster it's going to diffuse out. This is the idea of diffusion, going from smells, burnt popcorn from high to low, or whatever other stinky smell appeals to teenagers. And so we have this channel protein. This is like our doors and windows where we can open it and close it. All right, and so it's, things will move from high to low because certain of these proteins, and this is where we pull in the proteins from Unit 2, are very similar to these structures. So the proteins are, big globs of amino acids that help things to move in and out. And so active transport, this is where things start to get really tricky. This is where we move things from low to high. So we just stress that things move from high to low on their own. But if we want to move things from low to high, we have to do work. And so passive transport versus active transport, passive transport, things are going to move on their own. Active transport takes a little work to get them to move against that concentration gradient. So a lot of kids of this generation had these things called hex bugs when they were children. And they're just like these little like bugs that vibrate and they move everywhere. All right, so passive transport would be these hex bugs would move from high to low. If you had them all in a box, they all kind of move around randomly. If the box fell over, they would start to move from your box onto the floor all over the place. And so they are moving from high to low. Active transport would be where you have to use energy to move them against that concentration gradient. So you are now cleaning up the hex bugs. You got to go chase them down and pull them all back in. If kids didn't know hex bugs, we can go back to talking about like the mosquitoes or flies in your house. Like mosquitoes or flies will move from the outside area when it's very buggy outside to the inside area from high to low, but you are going to have to expend a lot of energy to move them out of your house. And so it's going to be much more active than passive. All right. So bugs moving into your house, passive. Bugs moving out of your house, active. It takes a lot of energy. Maybe if kids babysit, we might link this to like, toddlers in a preschool. They run all over the place and then like in the classroom, and then you let them out to recess, and then they will just randomly move. But when recess is over, we got to move them back in. That's going to take a lot more energy. You're moving them from low concentration into high concentration. You're condensing them back in the classroom from the playground. So when we talk about transport, talking about facilitated diffusion, active transport, diffusion. And so we kind of come back to this idea. You can come back to the ideas of the fences or the filters or the doors, but kind of this idea of how do things move from high to low. And also sometimes we have to move from low to high, so we have to expend energy. So that's kind of the day one lesson, and kind of the misconceptions where a lot of kids tend to come from is, you might say they move from high to low, but then you can move from low to high, but it takes energy. So it's adding this level of complexity. Then the day after this, we usually teach osmosis. Osmosis is extremely confusing to students because you're going to say things and they seem simple, and sometimes they can do it based on rote memorization, but sometimes they try to link it back to earlier things and it feels like it contradicts, but it doesn't, but it feels like it does. So osmosis, here's the definition I try to get to, is passive transport of water. So osmosis is only talking about the movement of the water, not the salt, not the sugar, but just the water across the semi-permeable membrane. Remember a lesson from the day before, semi-permeable rooms, things that let things in and out, from an area of high water, or from high water, which is low solute, to low water and high solute. This is where things get really hard, and we get back to this idea of comparison. So I used to start off with my story of whether or not you're tall or short. When we get into osmosis, we're going to use these words hypertonic and hypotonic. And these are comparison words, not definitions, but comparison words. So when I call myself tall or short, that is comparison to somebody else. I am average height. I am 5'10". My friend is the volleyball coach, and he is in the room next door. And I always just talk about, he would always call me short because compared to his volleyball players, I am fairly short. Right? When we coached youth sports together and we were coaching 5, 6, and 7-year-olds, we felt tall. I was a tall guy compared to my 5 or 6-year-olds, but I'm a short guy compared to the volleyball team. I did not change size. I did not shrink or grow. We're just comparing me to something else. So hypertonic, hypotonic, there's a lot of comparison of one solution to another. And so all of these terms now become relative. And so when we say things like high, low, hypertonic, hypotonic, this is all comparing to something else. So something is not tall or short. It's only tall or short when in comparison to something else. And something is not high concentration or low concentration. That's really only in comparison to other things. And so here's the other definition. I tend to come back to these complex definitions later, but this kind of helps some kids wrap their brain around things. So in osmosis, the idea we need is water moves from hypotonic to hypertonic solutions. If a kid just memorizes water moves from hypotonic to hypertonic, hypo to hyper, osmosis all kind of makes sense if they memorize it. But when they start to think about it, they start to get a little bit tripped up. So we're going to talk about two solutions. I'm going to give you some visuals. So normally we talk about this as being the one on the left is hypotonic, the one on the right is hyper. We say hyper is high salt or sugar, hypo is low salt or sugar. And we're like, good, that makes sense. Hyper, lots of salt or sugar, the little red triangles. Hypo, the red triangles on the left, a little bit less. Where kids tend to get mixed up is once we start to quantify these things, we'll put the measurements up there. But up here, we talk about hyper and hypo. Water, I'm going to fast forward a little bit, moves from hypo to hyper. Right? So water always moves to hyper, but hyper is high, hypo is low. And so what trips the kids up is we always use the words high and low without saying high water, or high salt and sugar to low salt and sugar, or high solute to low solute. So when I present this, I try to first start to talk, when we talk about solutions, there's two things, not just one. So you can't say a high solution or a low solution. We need to say either a high amount of water or a low amount of water, or a high amount of solute or a low amount of solute. So if we look at the diagrams here, kind of make it concrete, there's a lot of water on the left and less water on the right. There's a lot of salt and sugar on the right, very little salt and sugar on the left. And so this gives this idea of, hey, there's a lot of one thing here, but a lot of a different thing here. So now this is where we're going to start to talk about transport. Water wants to move from high to low, left to right, but salt and sugar also want to move from high to low, right to left, but it can't because there's a selectively permeable barrier in the middle that's going to prevent salt or sugar from moving directly across the membrane, right? And so now it's going to block it. So now we're going to label these things, right? Hypertonic and hypotonic. So when we talk about this, there's this barrier in the middle, right? And so on one side of the barrier is a hypertonic solution. On the other side is a hypotonic solution. Because again, these are comparison words, right? So our water still wants to move from left to right. But now when this cell is in a hypotonic solution, all of this water is going to be moving into the cell because the cell is now hypertonic by comparison. So now this is going to swell, all right? If we do the exact same pictures, but just flip which side is the inside of the cell, now water wants to move wants to move out of the cell and into the surroundings. So water's still moving towards hypertonic solution. No matter which of these two slides we're looking at, water is still moving towards hypertonic. It's just now the hypertonic goes from inside to outside. All right. And so I'll come back to these definitions. And it is very tricky for students. All right. And so I have some other images thrown in here if you guys want to use them. But when you say the words high and low, you always have to make sure you're talking about high water, high sugar, low sugar. High salt and sugar is hyper, low is hypo. And so when we always stress that word high and low, we're talking about salt and sugar. But what's moving is water, and water is the exact opposite of what the salt and sugar is. So this table on here shows like where, on the bottom, shows where this is really confusing for students. So students always want to go from high to low, and they forget what we're talking about. So water moves from high to low in osmosis, which means it's moving from high water to low water, which is a hypertonic solution, which is high sugar, low water, to hypotonic solution, which is low salt and sugar, high water. And so that's where things really start to get confusing.